You're watching the third lesson in Mix and Flow of Matter. This lesson will focus on separating mixtures. In the previous lesson, we talked about what mixtures were, how to make mixtures, and the different kinds of mixtures and how to tell them apart. In this lesson, we'll talk about how you can separate mixtures. What can you do to take the parts of a mixture and separate them? So remember that mixtures are combinations of different things, pure substances. Know what a pure substance is. Pure substance is something that is only made out of one type of molecule or one kind of atom. For example, a bar of gold only has gold atoms in it. A mixture has multiple atoms, different kinds of atoms, or different kinds of molecules. This also means that mixtures can be separated into their pure substance forms. One common example that we see every day is using a process called filtration. We see this every day, from making coffee to tea. So if we had a mixture where we had water involved, or a liquid involved, as the solvent, we can pass that liquid through a filter so that the solute stays behind. So know what a solute and solvent are. Solvent is the liquid that holds the mixture, or is the liquid that does the dissolving, while a solute is the solid part of the mixture that is either dissolved or in the liquid. For filtration to work, the solute needs to be too big for the filter to pass through the filter. So, for example, we have a mixture of sand and water. And if you remember from the previous lesson, this would be an example of a suspension. At first, it looks like a homogeneous solution. It looks like one thing. But over time, the sand will settle at the bottom. But let's say we don't have time to wait. So you can take this mixture of sand and water, put it in filter paper, and put it through a funnel. The water will pass through the filter. The molecules are small enough to pass through the filter and down through the funnel. The sand, however, is too big. The particles of sand are way too big. So they collect in the filter. And now you've quickly separated the mixture of sand and water. A real life example we see, coffee. When you make coffee, you use coffee filters. They collect the ground up seeds, the beans, and as hot water is passed through them, some of the beans get passed through the water, and those small particles fall into your glass, while the rest, the ground up beans, stay in your filter. And that way you don't get ground up beans in your coffee. Tea works the same way. Water passes through the tea bag, picking up very small parts of the tea, small enough to pass through the filter. However, the tea bag, the filter, doesn't allow the larger parts of the tea to pass through. Another example of filtration at work is our kidneys. So our kidneys are filled with these things called glomeruli. You don't need to know that fancy word, but essentially what happens is blood flows through here, and the kidney's job is to filter our blood. So what happens is materials move out of the bloodstream while the blood just moves on by. The blood cells are too big to move into this part of the kidney, so they just move on by and flow out. While waste products and water move out into the kidney. Now, some of it may get reabsorbed into the body, but waste just gets pushed through, and eventually that turns into pee. So this is a real biological example of how filtration works. Why would you want to separate mixtures? What would be the point of separating something that's already been mixed? Well, a really big example, and an important one, is water. Right? All life requires water in some way or form. But is all water drinkable? And you may think immediately, well, you can't drink ocean water. That's not good for you. You get thirstier when you drink ocean water. But the world needs water. So in order to make enough water for the rest of the world, you need to be able to separate the salt from the water. 70% of the earth is water, but less than 1% of it is drinkable or fresh. The rest is salt water. Again, water is needed for all life, including ours, especially ours. So to have enough drinking water, we need to remove that salt. We need to take the homogeneous mixture, that is salt water, and separate the salt from it. When you remove salt from water, it is called desalination. Saline, this word S-A-L-I-N, well, that is salt. De means to remove, and shun means an action. So it's basically removing salt action, essentially. So to remove salt from water, this process is called desalination. A process that can desalinate water is dehydration. Again, de, remove, hydrate, water, shun, action, to remove water. This process removes water through evaporation, right? So let's say you were in the middle of the desert and you needed water and all you had was a body of salt water. Well, you could dig a pit and you could collect the salt water and put it into two separate sections. You could create a collection bin in the middle, higher up, so that the fresh water doesn't flow back down into the salt water. You could take a sail or a tarp and put it over your big pit and put a weight in the middle. If you were in the desert, well then heat would cause water to evaporate, because when water gets warm, it changes state, and a change of state, it goes to gas. And then when it hits the sail, it can condense back into a liquid and drip right back into your collection bin. So water will just evaporate up, flow down, and fall into here. That's a process of dehydration. Heating water up and letting it recondense into another container. What could be a possible issue with this process? Well, an issue with this process would be, first off, you're relying on the environment to evaporate the water, so that takes time. Second, it's not a very fast process, right? So you're relying on the environment, it's a slow process, and you don't really collect a large amount of water. This would be okay if you were trapped in the desert, but it wouldn't be a really good process for mass producing fresh water. A way to mass produce fresh water would be a process called distillation. Distillation. This is one process where you actually add the heat yourself. And so it beats this process because you're adding the heat. You can add as much heat as you want, as much energy as you want. And so it can go as fast as you'd like it to go. And so if you have a collection of salt water here, the heat will cause the water to change state into gas, and it'll move up the beaker through this tube and into this section. This section is colder than this section. So as the water cools, it becomes liquid again and pours into another container. So another issue with dehydration is if you didn't have this top part, if this sail broke or if there was a hole in it, the water would just evaporate through it and leave, and you wouldn't be able to collect it. While with distillation, it's controlled by this tube, and the cold water pours into this beaker. So what is left after the water evaporates? Well, what's left is just salt. Water evaporates at a lower temperature than salt would even melt. To melt salt would take thousands of degrees. Water evaporates at about 100 degrees. So water will just evaporate out, go into the tube, and drip here, while salt will just be left behind. We call what's left behind the residue. Residual, residue, it's left behind. So the salt will be left behind, and the salt and the water will be here. And so you have a separated mixture of salt water. right? You started with salt water, you evaporated the water, salt is left over, and fresh distilled water is created or is moved from one section to another. So what if you had to separate three parts? In the previous situation, we had distillation of salt water, of just salt and water. What if you had salt water and oil? How could you separate oil and salt water? I'll now give you just a couple seconds to think about that as I will go over this in just a moment. So, salt water and oil. Well, you may first think, I'll just pour out the oil and then boil the salt water. Well, the problem with that is, how can you be so sure you've removed all that oil? Right? How can you be so sure that some of the salt water doesn't pour out with the oil? Nobody's perfect with pouring that liquid. So it's not a really precise way to separate these mixtures. One thing you could do is distillate this mixture, right? Again, when we looked at distillation, water boils and evaporates at a different temperature than salt. So the salt gets left behind. Well, what we can do is heat up the salt water and oil mixture so that the water leaves and it's collected in another container. Then you can increase the temperature and use another beaker to boil the oil, which will then evaporate and move into a different beaker. And what's left is salt at the bottom, water in another beaker, and oil in another beaker. Well, this is a process called fractional distillation. You're distilling different parts, fractional, which is different parts. You're distilling different parts in order to separate them from each other. So this is a type of distillation used by oil companies. It is used to convert crude oil, raw oil, into other types of useful fuels. And when we go back to this example, we use different boiling points to separate the water. Water boils at a different temperature than oil, and oil boils faster than salt. So first the water will go because it boils at 100 degrees, while the oil may boil at a higher temperature and move to its beaker at a higher temperature while the salt is left behind. With crude oil, well, crude oil is made up of different kinds of molecules called hydrocarbons. Hydro for hydrogen, carbon for, well, carbon. And in this example, you can see the black is carbon, the white is hydrogen, and there's a lot of them. And so crude oil is a mixture of complex compounds or molecules like this, as well as simple ones like this one, methane. Well, they're all jumbled together. They're all mixed in this black goo. How do I separate them? Well, this molecule here has a higher boiling point than this molecule here. This molecule will stay liquid at 100 degrees, while this one may turn into a gas at 100 degrees. So fractional distillation uses the different boiling points of these molecules in order to separate them. So you take the crude oil, you heat it up, and it enters this chamber. Well, the first thing to boil out would be this gas here, this refinery gas. It boiled at about 20 degrees. So with that heat, that refinery gas will just move out here and go through this chamber. And then at 70 degrees, petrol used in cars, let's use a different color, will boil up and move through here. Naphtha, used to make certain chemicals in factories and things, will boil at 120 degrees and move out here. Kerosene at 180, diesel at 260, lubricating oil at 300, fuel oil for like large factories and ships, And then what's left is residue, which can be used to make asphalt and roads. Each of these different chemicals are in crude oil, in this mixture. And they boil out at different temperatures. So using a different temperature, you can separate the different molecules based on their boiling point, right? Refinery gas will boil out first, then petrol, then naphtha, then kerosene, then diesel, then lubricating oil. And you won't mix these up because the petrol cannot go as high, the naphtha cannot go as high as the refinery gas because it's too cold up here. And it'll start to condense back down and stay gas in this area. It can't go down because it's too hot, and it can't go up because it's too cold. So it's stuck here, and it leaves through this pipe. Same with lubricating oil. The lubricating oil, let's use black, will boil up at 300 degrees, but it can't go up because it's too cold, so it'll go back down, and it can't go down because it's too hot, so it'll go back up, and it's stuck in this section, and then it'll be filtered out and collected. So using different boiling points, fractional distillation can separate the many different types of molecules found in crude oil. Without this process, we would not have fuel for cars and most vehicles we use on a daily basis. If your family has a car, without fractional distillation, we wouldn't have the fuel to run the car, unless you have a Tesla or an electric car. Certain boats that aren't electric use fuel, and airplanes use a large amount of fuel as well. So this is the process of separating mixtures and the importance of actually being able to and understanding how to. So you need to know, well, what a pure substance is. You need to know filtration, solvent, solute. Some of this is reviewed from the last lesson. You need to know why it's important to separate salt from water, right? All life needs water. So separating salt from water is important for us because we need fresh water. You need to understand that the process of removing salt from water is called desalination. And a process of desalination is dehydration. One of the processes for desalination is dehydration, which is heating up water so that it evaporates and condenses into another location. You also need to understand the issues with dehydration. You need something to collect that water, otherwise the water will just leave as a gas, as vapor. And this type of filtration takes a large amount of time. You need to understand what distillation is. You need to know how this apparatus looks like. You need to know that this beaker gets heated, the salt water evaporates, moves through this tube, and the fresh water condenses and is poured out here. You need to know what's left. You need to know what residue is. So in the case of water, you need to know that salt will be left behind while fresh water evaporates and moves away. You need to be able to think of ways in order to separate mixtures. You definitely need to know what fractional distillation is. Fractional distillation is the process of using different boiling points to separate mixtures, especially complex mixtures like crude oil. And that's it. That's the lesson. So, see you next lesson.